In this presentation, I will go over the details in an actual circuit simulation process and the actions taken by a circuit simulator. It is important to understand this process because it will give us insight on the potential problems during the simulation. For example, we will understand why a circuit simulation does not converge. It is also an important knowledge for model developer to understand the requirements for an efficient model. The circuit simulation is conducted in different phases. When an input DAC is presented to the simulator first sets up the simulation. It is called the setup phase. In the setup phase, the simulator reads the input and constructs the data structure for each device listed. It then allocates the memory to create the circuit matrix. After allocating space for the circuit matrix, the simulator calculates all the bias-independent quantities, such as kT over Q and other temperature-dependent parameters. The bias-independent quantities are treated as constant during the iterative process to find the circuit solutions. Following the setup phase is the solution phase. In this phase, the circuit simulator makes a guess for the node voltages. It then calls the device model routines to compute the matrix entries for the circuit matrix. It will look through all devices until all devices enter their contributions to the circuit matrix. Then, the simulator will perform iterations to solve for the node voltages and some branch currents included in the circuit matrix for this particular solution point. The process will be repeated for other solution points until all the solutions specified by the input range are solved. The final phase is to format the stored data to extract various information and display them in an easily understandable way to the person performing the simulation. The simulator can just output the raw data that the user can analyze them using more powerful third-party software packages. But more often, the circuit simulator also provides some simple plotting functions with some predefined user interface to display the data. This is not the core function of a circuit simulator and will not be covered in this presentation. To better understand how to set up the circuit simulations, let's look at an example. For the Colpitts oscillator shown in this figure, the input DAC is given on the left. It lists out the circuit elements one by one. By inspecting the terminals that the devices are connected to, the simulator will reserve memory space for a new entry to the circuit matrix when a new node is detected. The device data structure will then be added to a linked list to be called during the circuit simulation. In addition to the memory for the circuit matrix, the simulator will also reserve memory space to store some previous solutions that are required to project the subsequent results during the iteration. The bottom part of the input DAC contains the actions to be performed. They are just some commands to be acted upon. The data structure of the devices are explained in this slide. For each device listed in the input, it is associated with a model class. The model class is specified in this input file, which usually associated with a technology file specified by the technology providers. Graphically, the data structure is shown on the right. For each device reg, the circuit simulator creates its associated model. The model class contains the class name and the parameters common to all devices belong to the same model. All shared model parameters are processed here by the model-related subroutines. At the end, the model contains a pointer to the first instant data structure using this model. The instant data structure contains the instant-related parameters, which are unique to this particular device. These parameters are not shared with other devices of similar type. For example, If you have different resistors made of the same material, they will have the same temperature coefficients but different resistance. The temperature coefficients is stored as the model parameters, which is common to all resistors, while the resistance is stored as the instant parameter. The instant data structure also contains all the subroutines to calculate the currents and conductance generated by the instant, and enter them into the circuit matrix. At the end of the instant data structure, it contains another pointer pointing to the next instant sharing the same model. When another instance sharing the same model is read from the input list, they will be added into the linked list of the instant. When a device belonging to a different model is read, a new model data structure and a new instant data structure will be constructed. The data structure representing all the input devices are shown in the figure here. During the simulation, the device structures will be visited one by one following the pointers. Their internal subroutines will be called to fill in their contributions to the circuit matrix during the simulation phase. After setting up the data structure, evaluating the bias-independent parameters, and reserving memory spaces for the circuit matrix, the simulator entered the evaluation phase. In this phase, the simulator will follow the pointers to visit the device data classes one by one. The device data classes contain the data structure of the device and the device-related equations. The device receives the current estimates to the solutions or node voltages provided by the simulator. The model equations are called to generate the currents and derivatives based on the current estimates of the node voltages. Using the calculated currents and derivatives, the device enters its contributions to the Jacobian matrix and the current vector. The process will be repeated for each device following the pointers until all devices are processed. Then, the simulator will solve the linear matrix equations to find the next estimates to the solution. The process continues until all state variables converge to some deterministic values. This indicates one solution point is solved. One important requirement for a circuit simulator is fast simulation speed. The time spent by the simulator composed of the simulation setup time, the model evaluation time by the model subroutines, and the matrix iteration time. The setup time is in general linearly proportional to the number of circuit elements. The model evaluation time depends on the complexity of the model equations, and also scaled linearly with the number of devices in the circuit. The time for the matrix solution depends on the sparsity and the size of the matrix. In general, it is proportional to the number of circuit equations to the power 1.4, with some well-established sparse matrix solution methods. The most important contribution to the uncertainty in the simulation time is the number of iterations or the convergence in finding the solution. This has a strong dependence on the quality of the model equations of each device. A poorly formulated device model is the most common cause for non-convergence issues. To understand how a device model can affect the convergence during the iterative process, let's look at some examples that may result in poor convergence. As the iteration is mainly based on the Newton-Raphson method, the method only guarantees the iteration to converge to the solution if the initial guess is close enough. But close enough is very difficult to define. If the initial guess is far away from the solution point, there is no guarantee that the iteration will converge. Sometimes it may result in oscillation as shown in the figure here. In SPICE, the simulator allows initial conditions to be explicitly specified so that if we have some knowledge of the circuits to be simulated, we can help it to converge faster. Another cause for slow conversion is the error in calculating the derivatives. It will be illustrated in the given figure. It is not very common, but can happen in some dynamic or complicated functions that requires approximation to the derivatives. While in some rare occasions that it may help to improve the convergence if we are lucky, it will in general lead to slower convergence by making a less optimal increment for the next estimation. More seriously, some poorly formulated models may have discontinuities in their current voltage equations. It may not be caused by the device model formulation itself, but some devices like a switch do have abrupt transitions described by step functions. In this case, the solution and derivatives at one end of the breakpoint is inconsistent with the other end, leading to oscillations. To avoid convergence issue due to discontinuity in the device characteristics, sometimes smoothing functions are used to smooth out the abrupt transitions. In some models, the characteristics of a device may be constructed by piecewise functions to describe the operations in different regions. While the function can be made continuous by matching the values at the boundary, the derivatives can be discontinuous. It may lead to oscillations when locating the solution near the point where the derivatives are discontinuous. To avoid such problem, the device model should be both continuous and smooth. Ideally, it should be infinitely differentiable to avoid some undesirable behavior during simulation. Fast-changing functions, such as the use of exponential function, is another reason for poor convergence. Due to the quadratic convergence nature of the Newton-Raphson method, it may not be able to chase the change of the function, leading to poor convergence. An illustration is given here. The extremely steep slope causes an extremely small increment after overshooting from the initial step. In such a case, it will take a long time to approach the solution. Using the Newton-Raphson method to iterate with exponential function can potentially cause the value to overflow. As shown in this example, using a linear function to approximate an exponential function can cause a big step forward. Using the guess with such a large step can lead to a very large number that may overflow the numeric representation used in the computer. In order to handle exponential functions, some mathematical tricks are usually used to improve convergence. One approach is to use a limiting function to limit the step size for the next estimate. For the following example, a large step is projected using the current guess and its derivative. When this happens, a function is used to reduce or limit the step size. The limited step is taken to generate the next guess, relimit, for the iteration. The simplest way to implement the limiting function is to take half a step than what is predicted by the Newton-Raphson method. If the step is still too large, a logarithmic step can be taken using the formula given here. This represents the actual step size is given by taking the log of the step predicted by the Newton-Raphson method. For a linear matrix equation, it is possible to have no solution if the matrix is singular. It can happen when there is an open circuit. For example, the circuit on the right is perfectly valid, but the capacitor will cause an open circuit during DC simulations that will lead to a singular matrix. Another example is a function like what is given in the figure here, where there is a region with zero conductance. It will need to be extended to infinity before the derivative can cross the x-axis. To prevent some of the important Jacobian matrix entries to become zero, a small number G min, representing the minimum conductance, can be added to some of the zero matrix entries to prevent the Jacobian matrix from becoming singular.
As the last example for potential problems during circuit simulations, we will discuss some bistable circuits, which may have more than one solution point. For example, we may look at a ring oscillator circuit as shown in the figure. While the simulation should drive the circuit to oscillate, there is an unstable equilibrium solution with a value equal to half of the supply voltage. It is possible that all the node voltages just stay at this intermediate value and the oscillator will not oscillate. In reality, this is an unstable equilibrium that a small noise will be able to get it out from this point. It is like a coin standing at its edge, which is possible, but some small noise will get it out from such situation. In a simulation, a small perturbation will be able to help the circuit to get out from such situation. For example, introducing a small step from -0.1 volt below VDD to VDD to the power supply voltage in the beginning of the simulation. That will get the circuit out from the unstable equilibrium point. This is the end of this module, and by now you should have some understanding about the actions of the circuit simulator when a circuit simulation is performed. This knowledge is important to understand the requirements of a good device model for efficient circuit simulations.